So let's practice the concept further using this example. So the mean price of a product obtained by sampling it on 100 randomly chosen days was 980 pounds. Assume that this price follows a normal distribution with standard deviation of 280 pounds. Construct an 80% confidence interval for the mean price of this product. Okay. So the question is asking us to find the 80% confidence interval for this particular value mu, which is the mean price of a product. So in order to find such a confidence interval, we first want to define the significance level alpha. So remember that alpha is the opposite of the confidence interval. So in this case, alpha is 1 minus 0.8 because we want to construct an 80% confidence interval. So the significance level alpha is 0.2. Okay, and we want to find the z-score that corresponds to alpha divided by 2. So here alpha divided by 2 is 0.2 divided by 2 is 0.1. And we want to find the z of alpha divided by 2, or in this case, z of 0.1, which is the probability of this z being between 0 and z of 0.1 is 0.5 minus 0.1, which is equal to 0.4. So we want to find this z value of 0.1 such that this entire probability is equal to 0.4. And using the table, we can find that the z values that corresponds to 0.1 such that the probability value has a 0.4 is 1.28. Okay, so now that we have figured out this particular z-score such that the probability of the random variable z being between 0 and z of that value is equal to 0.4, we can plug in this value in terms of in place of the confidence interval equation. So remember that the confidence interval, in this case, 80% confidence interval for the mu is defined using this lower bound and the upper bound. So the lower bound is defined by x bar minus the z of 0.1, in which case we identified this as 1.28 times sigma divided by square root of n. And the upper bound is defined as x bar plus 1.28 times sigma divided by square root of n. And here, the question also gives us the specific value for the sigma, the population standard deviation, which is 280. And we know that the sample size is 100. So after plugging in all these numbers, and also we know that the x bar, the sample mean, is 980. So after plugging in all these numbers, we can just do the calculation, and then we can find the confidence interval, or the 80% confidence interval for the mean price of the product, which is 944, 1015. So next, I want to move on to the case where we want to find the confidence interval of the population mean mu when the standard deviation for the population, which is sigma, is not known. So in previous examples, that when we want to define the confidence interval mu, we had everything. So we had x bar, which is the sample mean, and we also had the sigma, which was the population standard deviation. But I briefly mentioned how it's very unlikely that we would know the actual standard deviation for the population, which makes sense given that like if we don't know the actual mean of the population, then it's very unlikely that we know the actual standard deviation of the population, right? So this case is actually more representative of the real world. So what do we do if we don't know the actual population standard deviation? Like what do you plug in like when we in place of sigma? So I'm not gonna go into details of the proof behind why we can use this sample standard deviation S in place of this population standard deviation sigma, but I will show that we can do something very similar to what we have done when we didn't know the population mean mu, then we substituted the population mean with the sample mean x bar, right? So instead of the sigma, the population sample population standard deviation, we can substitute sigma with S, which is the sample standard deviation. However, when we substitute the sigma in place of, when we substitute S in place of sigma, then we have an additional complication that this entire distribution does not follow a normal distribution. So we can't use the normal distribution table and the normal distribution function to identify the z-scores. But instead, we can use a different distribution, which is called the t-distribution, which is very similar to the standard normal distribution in certain cases. So t-distribution looks something similar to the normal distribution, except it has one additional parameter. So here, if you compare the shape of the standard normal distribution, that's at that's aggregated more at the center versus the t-distribution, then you see that like these two look similar, and for certain cases of degrees of freedom, you will see that these two distributions actually look very similar. Okay, so in case of when we are not given the population standard deviation, we can still use a formula for the confidence interval that looks pretty similar to our previous formula. So here you see that everything stays very similar, except instead of looking at the z-score, you have to look at the t-score. And then we will talk shortly about how to find these t-scores, and we will talk more about the t-distribution. And then you also notice that in place of the sigma, you have S that substitutes sigma, which is why you're using the t-distribution instead of the normal distribution. And remember that this t-distribution is different from the normal distribution in that instead of having two parameters like the normal distribution, t-distribution has one additional parameter, which is called the degree of freedom, or sometimes we call it df. So degree of freedom is pretty easy to find. So degree of freedom is just defined as n minus 1. So where n is the number of the 다시 할게요. So the degree of freedom is defined as n minus 1, where n is the sample size. So here let's talk about how to calculate the t-score. So this is pretty similar to how we calculate the z-score. So instead of the standard normal distribution table, we use the t-distribution table. And here, for different t-score, you have, and for different degree of freedom, you have different t-scores already calculated. For different t-scores, you already have different probabilities already calculated that represents the area under the curve that's on to the right tail side of the particular t-value. Okay, so for example here, if you want to find the t-score such that the significance level is alpha, where alpha divided by 2 is equal to 0.05, which means the significance level alpha is 0.1, then how do you find the t of 0.05 with the sample with 4 degrees of freedom? So you can find that exactly from the table by first going to the row, which represents different degrees of freedom. So you go to row 4 with the 4 degrees of freedom, and you find the corresponding t sub 0.05 value. So in which case, you can find that the t sub of 0.05 is equal to 2.132. So that's how you use the t distribution table that's analogous to using the standard normal distribution table for finding the z-scores or the t-scores. All right, so we're gonna go over some more exercises to practice the central limit theorem and how to apply these for finding the confidence interval. So the first exercise is as follows. The mean price of a product obtained by sampling it in 100 randomly chosen days was 500 pounds. So assume that the product's price follows a normal distribution with standard deviation of 50. So construct the 95% confidence interval for the mean price of the product. So here we have the population, which is the price of a product. And then what we're ultimately interested in this question is the mean price of the product, which we will call the mu. And we want to construct a 95% confidence interval such that the mu lies in between these intervals and 95% of the time. And using the previous equations for finding the confidence interval, we first know that the 95% confidence interval for mu, or we can just easily or simply call it CI, is an interval that has a lower bound of x bar minus 1.96. So remember that this number comes from the fact that we have a 95% confidence interval. So for example, like if you had a different significance level other than 0.05, then you will have a different number in place of here. But anyways, in this case, we have a 95% confidence interval, so we can just use a number 1.96. So x bar minus 1.96 times sigma square root of n, and the upper bound is x bar plus 1.96 and sigma divided by square root of n. And the sample mean is also measured as from the question. So we are given that the sample mean is 500. So when you took a random sample from the population and you measured the sample mean, it was 500. And the population standard deviation sigma is also given. In this case, it's given as 50. So remember that, so in this case, because we are given the actual true population standard deviation sigma, so we could just use this 95 z-score, the z-score value for measuring the confidence interval. But later we also learned that if we are not given this population standard deviation sigma, then we would have to substitute this with a sample standard deviation S, and we can't use the standard normal distribution z-score, but we instead have to use the t-score. But anyways, in this case, we are given the sigma, so that's 50, and the n is the number of sample, which is 100. So now we're done because we have all the quantities that's given from the question. So if you just calculate these values, and you have 490,509. So in other words, let's try to interpret this interval. So this is the confidence interval, 95% confidence interval for the product price meaning that there is a 95% chance that the actual mean of the population, which in this case is the mean price of a product, lies in between this interval. Okay, so in today's lecture, we talked about sampling. So we talked about how the purpose of statistics is to know the quantities of the population, in particular the population mean and the population standard deviation, mu and sigma. However, because usually it's not possible in reality to measure all the quantities of the entire population, what we do is sampling. So we draw a random sample from the population and then we measure the quantities of particular sample, and then we try to draw some, make some inference about the quantities of the population. And the way that we do it is by using the central limit theorem. So central limit theorem basically connects the quantities of the sample with the quantities for the population. So basically, if we know the quantities from the sample, like the sample mean or x bar, then we can make inference about the range of possible values of mu, the population mean, which is basically given as a range. So that range is called the confidence interval. So we have different degrees of confidence. So for example, like if you want to find the 95% confidence interval, that means that the mu will lie within that interval for 95% of the time. So we also learned how to derive such confidence interval using the formula. And then we also learned special cases where we do or do not know the actual value of the population standard deviation sigma. So this is what we have learned so far, and in next class we will continue our discussion on statistical inference. Right, so I'll see you guys next week.